expansion theory features that are still experimental but are under active development. So if you want to describe a quantum process from first principles, where would you start from? So you go to the library, you take a book in quantum mechanics, and you see that the most fundamental equation that is supposed to describe the physical reality at the quantum level is the time-dependent Schrödinger equation. For a system of interacting electrons whose coordinate I indicate with lowercase r, and nuclei whose coordinate I will indicate with capital R, the Schrödinger equation says that the time derivative of the wave function is equal to the Hamiltonian applied to the wave function, where the Hamiltonian is made of a nuclear kinetic energy contribution, an electronic kinetic energy contribution, and a rather complicated potential, interaction potential that depends at the same time on electronic and nuclear degrees of freedom. This is a very complicated equation, of course, that cannot be solved in practice on any computer, but for hyper-simplified models. And the first very important approximation that is used to solve this equation is the Born-Oppenheimer approximation. I will not say much about this, but just state a few facts and state the origin of the approximation. The origin of the approximation is that the nuclear masses are much larger than the electronic masses. If the nuclear masses were infinite, which they are not, of course, but if they were infinite, this term would vanish. So the Schrödinger equation would simplify immensely, basically because if this kinetic energy nuclear kinetic energy would vanish, then the Hamiltonian operator would not be a differential operator with respect to the nuclear coordinates. It would be differential only with respect to the electron coordinates. So the nuclear coordinates would just act as an external parameter. And you could solve the Schrödinger equation at fixed nuclei, fixed because they do not move because they are infinitely heavy. And you would have basically half as many roughly half as many as the degrees of freedom as for finite nuclear masses. The finiteness of the nuclear masses is such that, with some theory that I will not say anything about, you can, to lead in order in the ratio between the electronic to the nuclear mass, you can demonstrate that you can map this quantum mechanical evolution equation into a pair of equations, the first of which is classical for the nuclear degrees of freedom. Classical in such a way that you have basically the Newton equation of motion with an effective potential acting on the electrons that is nothing but the eigenvalue of the time-independent Schrödinger equation that you would obtain if the nuclear masses were infinite. So the logical step is, first, let us assume that the nuclear masses are infinite. You drop this term and you map this time-dependent Schrödinger equation into a time-independent eigenvalue equation, which of course depends parametrically on the nuclear coordinates. So you have eigenfunctions and eigenvalues that depend on this external parameter that are the nuclear coordinates. You take this eigenvalue as a function of these parameters, of the nuclear coordinates, and you plug it into this Newton equation of motion. The coupling of the two gives the leading order of the time evolution of the quantum system in the ratio between m, between the electron to the neutral masses. By the way, this is exactly the kind of approximation that is implemented in modern ab initio molecular dynamics techniques such as Scarparinello that you will learn about next week. Of course, as powerful as the Born-Oppenheimer approximation is, it still leaves behind a very complicated time-independent Schrödinger equation to solve. The main complication arises from the presence in the interaction potential of the electron-electron interaction. So basically, the potential energy to which the electrons and the interacting electrons and ions are subject is made of three terms. A nuclear term that, from the point of view of electrons, is just a constant, right? So this is just an additive constant that sets the zero of the electronic energy. Then you have the interaction of the electrons with the nuclei, which is not so difficult to deal with because you can deal with this term in the independent electron approximation. So you can solve the Schrödinger equation for each electron at a time and not for all of them at the same time. Problems arise because of this electron-electron interaction term that hinders our ability to factorize the wave function, the total electronic wave function, into a product of single particle wave functions, and makes the problem basically untractable from a numerical point of view. So density functional theory is, we will see in a while what it is about, but basically it amounts in practice to replacing this electron-electron interaction with an effective one-body electronic potential that depends parametrically on the density, that is defined as the sum over the one electron orbitals of the one electron, sum over one electron states of the square modulus of the orbital. So basically, if you replace the potential, the complicated many-body potential with a one-body potential, then the resulting Schrödinger equation can be factorized for the wave functions of individual electrons. These individual electrons carry a contribution to the density that is basically the square modulus of each one of those orbitals, and the sum of those contributions gives the density upon which the potential depends in a self-consistent way, in a fashion that we will see in a while. Let me make a very short and shallow detour in mathematics, just to make sure that the basic concepts the basic mathematical concepts upon which DFT relies are known to everybody. So density functional theory is about a functional. What is a functional? In mathematics, a functional is nothing but a map, a mathematical map, a function whose domain of definition is not a space of numbers or a space of vectors, but it is a space of functions, right? So if you have any rule that allows you to univocally associate to a function in some defined functional space to a real number or a complex number, this is a functional. A functional is a function of a function, not a composite function. It's a function whose argument is a function. Let us see a few examples of functionals. For instance, if you take a functional space of one-dimensional functions or functions defined on a one-dimensional domain, for instance, a functional can be taken as the value that the function acquires at some point in the domain of definition. One possibility. Take the space of all the functions defined in the interval 0 and 1, and you say that the functional that you are interested in is the value that the function acquires at x equal 0.5. Why not? Or else, you can take as a functional the value of the integral over the interval of the range of definition of the square of the function, or the square of the derivative, or you name it. You give any rule that allows you to return me a number once I give you a function that is a functional. Okay? Of course, in order for the concept of functional to be useful in practice, you have to know how to implement it on a computer. And functional spaces are usually spaces of infinite dimension, and computers are finite machines. So if you want to instruct a computer how to deal with an object that lives in an infinitely dimensional space, you have to do some approximation. So one possible approximation for a functional would be to represent the functional, to represent the function that is the argument of the functional by the values that the function acquires at discrete points in the range of definition. For instance, you can approximate the function f of x as a vector f1, f2, fn, that is the collection, the argument of the functional is this collection of values that it acquires at discrete points. Then the functional will be a function of this set of points, set of values, right? So the functional can be seen, the approximation of the functional can be seen as a function of many variables, right? It is a function of the values that the argument acquires at the points that represent the discrete point that represent the function. There are other ways of approximating functionals. One other way that is say intuitive, at least for people accustomed to quantum mechanical methods, is to expand the argument of the functional into a set of into a basis set, and then the argument of the functional would be uniquely determined by the coefficients of this expansion. Then the functional would be a function of these coefficients, right? This is all about the practical implementation of the concept of functional as a function of an argument that lives in a space of infinite dimensions and of a continuously large number of dimensions. So this is all about approximating this with functions of a finite number of dimensions. Functionals are useful concepts because it is upon these concepts that we base many variational principles. DFT itself is based, as we will see, on a variational principle. So basically, functional calculus is, or the calculus of variations, is aimed at finding functions that make functionals stationary, minimum, maximum, or extremum. If you were to solve these extremum problems with functions of a finite number of dimensions, what would you do? You would search for minima, maxima, or saddle points. And in order to look for minima, maxima, or saddle points, you will have to find places in the domain of definition of the function or functionals where the function or the functional has zero derivative. The gradient of the function has to be zero. So it is important to generalize the concept of partial derivative. If you have a function of many degrees of freedom, then you can define partial derivatives. If the number of degrees of freedom becomes infinite and continuous, then you have to replace the concept of partial derivative with the concept of functional derivative. Let us see what a functional derivative is. Suppose you have any functional that I call g, and the functional is a way of defining a number in return to any function of a given functional space. Now, suppose you take two fixed functions in this functional space, f0 and f1, that are fixed once for all. And you take a linear combination of the two with a number epsilon. This number here is a function of epsilon, right? Because f0 and f1, they are fixed. So once they are fixed, this is a function of epsilon. This function of epsilon can be Taylor expanded, and you have a term that is of order 0. Of course, of order 0, when epsilon is 0, the value of the functional is g of f0. And then you formally make a Taylor expansion. There will be a linear term. Because it is linear, it cannot be anything but the integral of f1 times some function. This function is by definition the functional derivative of the functional. Okay? So the functional derivative of a function is defined by the linear term in the Taylor expansion of the functional in powers of this small term, small coefficient. Of course, you can ask yourself, what about the correspondence that we have made a slide ago between functionals and functions of many variables? If I discretize the argument of the functional, the way we did one slide ago, of course this functional would become a function of these very many values of its argument. And you will easily see, I will not say anything about this, but it's enough to think a little bit about definitions, that